Hi, everybody, and welcome to Linear Algebra. Well, here we first thing I'm going to do is share my screen with you, and here we go. Now, we're going to our course, as you know, is using Linear Algebra by Larson, 7th edition. I have it as a PDF, and but that's the book. Anyway, we're gonna go through chapter 1 relatively quickly because most of chapter 1 is stuff that you did just in high school algebra. But there are a few things which are going to be more relevant to the linear algebra course, and that, of course, I'm going to spend a little more time on. Anyway, this is 1.1. So a linear equation in n variables. This is now notice here it says a linear equation in n variables. And a list of variables, x1, x2, x3, so forth. You would normally, in high school, you would say x, y, z, w. The problem is that if you have 20 if you have an equation with like 50 variables, you start running out of letters and stuff, and and it gets unwieldy. It's actually easier to keep track of things if you just use subscripts. So x1, x2, x3 is what you used to call x, y, z. And I'll kind of use both interchangeably. Anyway, a typical linear equation is of the form ax1 plus a1x1 plus a2x2 plus a3x3 dot 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 plus an xn equals b. By the way, dot dot dot. If I had to give a theme for our linear algebra class, it's going to be dot 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 because that comes up quite a lot. Anyway, so the coefficients, we give them subscripts to match the variables. Again, it makes things kind of really easy to keep track of stuff. A1, of course, is what they call the leading coefficient. I'm sure you've heard that term before. X1 is a leading variable. And B on the other side is the constant term. Now, of course, the A's and the B are all just regular, like real numbers, just plain old numbers. But for some reason, when it multiplies a variable, you call it a coefficient. When it sits up by itself, they call it a constant. Don't see why they do that. Okay, so linear equations have no now linear, of course, is from the word line, like a straight line. And now, of course, if it's 3 variables, it won't be a straight line, it'll be a straight plane. But you get the point. Anyway, these are all linear equations. 3x plus 2y equals 7, 1/2 x plus y minus pi z equals radical. Even though pi and rad 2 are irrational numbers, it doesn't matter. But x, y, z are just plain numbers. Sine pi, now sine pi is just a constant. Hey, it's actually 0 now that you think about it, but it doesn't matter. Sine pi, cosine pi, it's just a constant. And so sine pi times x1 minus, what I'm trying to say is that if you had an equation with sine x is not a linear equation, but sine pi times x, that is linear because sine pi is just a number. And here's some equations that are not linear. Why is it not linear? Because you have x times y. See, if it was just x plus y, that would still be linear. But when it's x times y, that makes it not linear. E to the x minus 2y, the e to the x part is not linear. X sine of x is not linear. And of course, like x squared, x to the third power, or anything like that, those are not linear. Basically, generally speaking, linear equations, when you graph them, they're straight lines or straight planes or straight whatever. But they just have plain old x's and y's and z's, not multiplying each other, not having powers, so on and so forth. Again, I'm going through this kind of quick because most of this is just stuff you did in high school. A solution, the technical definition of a solution is that it is the technical definition of a solution is that it is a sequence of numbers, and if you substitute these numbers for the different variables, the equation becomes satisfied. That's a very fancy way of saying plug in these numbers and everything works. Now, here's something which you may or may not have done in high school. Some of you may have done this in pre-calculus, but the idea of a parametric representation, because you know that like when you have a system of more equations than more variables than equations. When you have more variables than you have equations, you know that you wind up having, and we're talking about linear equations, you know you wind up having infinite solutions. And even though it's infinite, but infinite is not just random, because see, if I would just say that there's infinite solutions, that doesn't mean I can pick any random numbers and that's going to solve it. There are still certain restrictions, and parametric representations is where this comes in. So, for example, here's an equation: x plus 2y equals 4. See what I did there? I said x plus 2y. Instead of saying x1 plus 2x2, I said x plus 2y. It's the same thing. And I'll kind of use those things interchangeably. Now, even though there's infinite solutions to this equation for x and y, it doesn't mean that I can just pick any two random x and y. I can't say x equals 5 and y equals 12, because that would give me 29 instead of 4. Now, I could do x equals 2 and y equals 1. That would work, but not everything is going to work. And so I can't just randomly throw in x's and y's and get solutions. But I can make it parametric so that I can just throw in numbers and get solutions. What am I going to do? So whenever you do parametric, what we do is we decide on one variable that we call free. Sometimes it's called independent, and the other variable would be dependent. Now, or in this case, now, it really doesn't matter. It often doesn't matter. You could choose either one to be free. In this case, if I write it this way, x1 equals 4 minus 2x2. So I have x is equal to 4 minus 2y. That was just convenient because I have an x by itself. I could have let y be the free one. It doesn't matter. But anyway, sticking with this, if I let the other variable be the independent variable, I'll let y be the independent variable, and I choose something called a parameter, which is t, and I let y equal t, then the solution set would be x equals 4 minus 2t, you see on the bottom, and y equals t. Now, what's so great about this? What we did a bunch of work to do this. What's the point? The point is that all I got to do now, I can just randomly stick in values for t. And every time I randomly stick in a value of t, I get a different solution, x comma y. For example, if I let t equal 1, that's going to give me the solution 2 comma 1, which is a solution. And if I let t equal 4, that's going to be 4 minus 8, which is negative 4, and y is going to be 4. So that gives me the solution negative 4 comma 4. The point is, I couldn't just randomly pick x. So why do I need parameters for? Because without parameters, I can't. As I said before, I can't just randomly pick x, y variables, but I can, because not every x and y are going to match. But I can randomly pick t, plug the t in to the parameter thingy ding, and get all the x, y solutions I want. And now, of course, we could have chosen let x1 be the parameter s, and then x2 would be 2 minus 1 half s, and that would wind up being the same thing. That would wind up giving me the same. Again, I could just stick in. For example, if I would let s equal 1, what would I let s equal? If I would let s equal 2, then that would give me 2 comma 1. So that, which is the same xy solution I got when I let t equal 1 just a minute or two ago. Anyways, that's how it works. So here we have a problem. We want to find a parametric representation of a solution set, and we want to solve the linear equation 3x plus 2y minus z equal 3. So what are we going to do? So again, I have a choice. I want y and z to be the free variables, and I want to solve for x. So now I'm gonna need two parameters. See, before it was either s or t. Now I need two parameters. Generally speaking, if you look at the number of variables, minus the number of equations, that's going to tell you how many parameters you need. In other words, in this example 3, there are 3 variables and 1 equation. 3 minus 1 equals 2. And that's why I need 2 parameters. And that's just, you'll see, that's just going to make a lot of sense. Anyway, I'm letting z equal t. I'm letting y equal s. And now x is equal to 1 minus 2/3 s plus 1/3 t. And that I'm just solving for x, in terms of the other 2 guys. And now, if you just give me any random s and t, and not only that, not just any random combination of s and t, that'll produce a triplet, an XYZ triplet that is a solution to this equation. So for example, if I let s and t each equal 0, then that's going to give me the solution 1, 0, 0. If I let s equal 1 and t equal 2, that's going to give me the solution 1, 1, 2. And but the point is I could randomly pick variables for my parameter. I could just plug away. Okay, next is going to be systems of linear equations. A system of linear equations, it just means you have a bunch of linear equations all together. But it's not just that I'm taking a bunch of linear equations and stacking them up like this. It means that, you see, here's the key, here's the cruncher. A solution of a system of linear equations is a sequence of numbers that is a solution for each of the linear equations in the system. So for example, if I can have, let's say this guy right here. Let's look at this guy right here. If I would have x equals 1 and y equals 0, that will be a solution for the top equation, but it will not be a solution for the bottom equation. So x equals 1 and y equals 0 is not a solution for the system. On the other hand, if I have x equals -1 and y equals +3, then that will be a solution for the system because it satisfies both equations. And that's the thing about systems. In a system of linear equations, it's not considered a solution unless I solve all of them. So they're all one big happy dysfunctional family. Okay, I think that's is that it for this? No, there's more. Well, these are just systems. Okay, now this is kind of cool here because each of these 3 problems, A, B, and C, are actually very different. Systems, because in problem A, I could solve that very easily with high school algebra, and I get x equals 1, y equals 2, and that's my solution set. So I have one solution. If I would graph this, I would have 2 intersecting lines. I'm sure you know that. Now for B, there's actually infinite solutions. If I would graph this, I would find basically any solution for the top equation in B is going to also work for the bottom equation in B. In fact, you could see that, if I just take the top equation and multiply it all by 2, I get the same thing as the bottom equation. It's kind of like, so this would be like 2 lines like on top of each other. And finally, a problem C, that's going to have no solutions because, and if you graph that, you get 2 parallel lines. X plus y equals 3, x plus y equals 1. That would, by the way, if you subtract, in number 3, if you would subtract the 2 equations, I would get 0 equals 2, which is false. So whenever you get something that's false, that always means no solutions. 0 equals 2 is false. On the other hand, if I would, in problem B, if I would, let's say, multiply the top equation by -2, so I have -2x plus -2y equals -6, and then add the 2 equations, I get 0 equals 0. 0 equals 0 is true. When that happens, that's when you're going to have, as all the variables drop out, you're left with the true statements. That means you're going to have no infinite solutions. Okay, and that's what we have right here. And this is graphs of all that. And this is something which I'm not going to prove now. We will prove this eventually. But for now, we're going to say the number of systems of a system of linear equations. For a system of linear equations, precisely one of the following is true. It either has one solution, infinite solutions, or no solutions. Precisely, the word precise here means at least one of these is always going to be true, but only one of these is always going to be true. It means anytime you have a system of linear equations, there's either going to be one solution, no solutions, or infinite solutions. That's, in other words, you'll never have three solutions. You'll have none, one, or infinite. You'll never have 17 solutions. It's either zero, no solutions, one solution, or infinite solutions. Those are the only choices. It's always going to be one of those three, and you will never have more than that. Okay, I want to go for. Okay, we're back on the air now. When you, I'm not going to go into solving systems of linear equations. You did plenty of that in high school, but I will say this is just common sense, or I shouldn't say common, it's common knowledge that when we do solve a system of linear equations, there are three things that we do. We interchange two equations. We do that sometimes. We multiply an equation by a non-zero constant. That's something we do. Or we add a multiple of an equation to another equation, meaning I'll take an equation, multiply it by -2, and add it to the other equation. Sometimes if I have three equations, I want to put two, I want to switch the order of them. That's what interchanging equations means. So these are just things we do. It's commonly done. It's common knowledge. And that's all we're going to do on 1.1. And it's been a pleasure. Wait to see you in the next video.